Welcome to this week's AI Talks. Today we have the immense pleasure of hosting Professor Cynthia Rudin, who is a computer science professor at Duke University, but also a professor of a number of affiliated fields. There, she directs the interpretable machine learning lab, and this is her work that I know the most. And over the years, I've come to really admire her ability, or the ability of her group, to tackle both challenging technical aspects of machine learning, like optimization and so on, as well as making machine learning ready for application use in the real world. But of course, I'm not alone in admiring these aspects, because Cynthia's won numerous awards for her research in interpretable machine learning, and recently she was awarded the AAAI Squirrel AI Award for artificial intelligence for the benefit of humanity. I'm very excited to hear what she has to say today. So with that, I'm not going to take any more time, but instead hand over to Professor Rudin. Please go ahead.
Thank you. Okay. There we go. You should be able to see my slides now.
Perfect.
Okay, great. So I want to start with a question, which is, can a typographical error lead to years of extra prison time? Right? This should never happen, right? Like typos making decisions, that's crazy, right? You know, who's making a decision here, a judge or a typo? And would it be fair if that happened? But it happens all the time. And this is an article in the New York Times about Glenn Rodriguez, who was denied parole because his COMPAS score was miscalculated. And COMPAS is a black box proprietary model that predicts future crime. And it's used in parole decisions. And he only realized after the decision was made that there was a typographical error in his criminal history features. And so, yes, a typo made a decision here, not a judge, not a parole board, a typo. And he got years of extra prison time. So some definitions. A black box model is a formula that's either too complicated for any human to understand or it's proprietary. And that stands in contrast to an interpretable machine learning model, which obeys a domain-specific set of constraints so that humans can better understand it. So why do we need interpretable machine learning? We need it for high-stakes decisions or troubleshooting, right? Anytime it would be really bad if the model went wrong. Because a lot of times AI models do go wrong. They go really wrong. So, okay, what else could go wrong with a black box? So we already know that we could send people to prison based on typos, but what else could happen? And I put up two of my favorite articles where black box AI models went wrong and no one was able to figure out what happened. So the article on the left is about a black box AI model that told everyone that the air quality was fine during the wildfires and that it was safe to go outside when it was not. And the article on the right is about how an FDA-approved deep learning model for detecting intracranial hemorrhage was launched into the world, and then it didn't perform very well. So you have all these hospitals using this model that was approved by our Food and Drug Administration, and yet it didn't work in the real world, and no one knows why. Now, I've given you just a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong, and probably many things have gone wrong that were hidden, and so I don't know about them. And now people are starting to use machine learning for medical decision making, for loan decisions, for self-driving cars, and all manner of other things that you really don't want to go wrong. And some people love their black box machine learning models. They argue fiercely that they need them. Anyway, so I want to get back to COMPAS. So do we really need to have black box models? Are they more accurate? And luckily, there was a data set from Florida that was released a while back that could tell us exactly how accurate COMPAS is. So we took the data from Florida and compared it to a method, our latest machine learning method in the lab at the time. Okay, so the data set had COMPAS scores, and it had basic criminal history information and demographic information from a few thousand people in Florida, okay? And the algorithm that my lab had developed is called corals. We've gone past corals now. We've developed corals into something bigger, but corals is a very complex algorithm, but it produces very simple models. And in fact, the model that corals produced on this data set was so tiny that I can put it in the corner of a PowerPoint slide. Okay, so here's the machine learning model that corals produced. It said If the person is 19 to 20 years old and they're male, then predict arrest within 2 years of their compass score calculation. Else, if they're 21 to 22 years old and they have 2 to 3 prior offenses, predict arrest within 2 years of the compass score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. Okay, that's the whole machine learning model. And we thought, could this really be as accurate as compass? And it was. So we always do tenfold cross-validation. So the different colors are different subsets of the data, different test folds. And we thought, okay, well, they're about equally accurate. Well, that's interesting. Well, I wonder what would happen if we tried to throw the entire machine learning arsenal at this problem. Could we get more accuracy? So we tried a whole bunch of different machine learning methods, and they all performed about equally accurate. And some of them are complete black boxes like compass, right, where we don't know what's in it because it's proprietary. Or some of them are really complicated to the point where you cannot put the formula on a slide because it's really complicated. So for example, boosted decision trees support vector machines with radial basis function kernels. These are very, very complex formulas. Whereas on the other extreme, the Corals model is just right here. So there was this huge debate about algorithmic fairness of compass, whether it's fair. But the truth is that we just don't seem to need compass at all. Okay, now you've seen that black box models are not always more accurate than simple models, but there's some more important kind of general knowledge that I need to provide you. There's really two broad kinds of problems that we encounter in machine learning and data science. There's problems with tabular data and problems with raw data. So tabular data look kind of like the criminal justice data I showed you. This is a medical example here where you've got features and either categorical or real valued values for the features. And then for raw data, that data is like different. So this is like, for example, image data where say 1 pixel would not give you any information really about what is in the image. And then sound waves or large amounts of text. And these two types of problems are very different from each other, both in terms of what algorithms work and the definition of interpretability. So for instance, so in terms of the algorithms, for raw data, the only technique that's really working right now is neural networks. And that's not necessarily the way it's always going to be, but that's how it is right now, okay? Whereas for tabular data, that is not true. For tabular data, as long as you're willing to do some pre-processing, all the methods tend to have similar performance, like I showed you with the Florida data. And what that means is that you can often construct really sparse models, like little decision trees like the Corals model I showed you, or scoring systems, or some other tiny little thing that gets you to the performance of the best black box that you could construct. And then also the definition of interpretability needs to change. So here, for instance, you could have a sparse model, not, humans only handle a certain number of cognitive entities at once, right? 7 plus or minus 2. So sparsity works here, but not here. So you have to think about what is the right definition for interpretability. So I want to talk about tabular data for a little while. So tabular data, as I mentioned, the fact that you can get very interpretable models on tabular data without losing accuracy, that gives you an opportunity, right? But you have to optimize the models really well in order to get up to the accuracy of the black boxes. And so I want to give you 2 examples of machine learning in high stakes decisions with tabular data. And the first example is going to be about taking care of critically ill patients. And the second one is going to be about electrical grid reliability. Okay, so let's start with preventing brain damage in critically ill patients. So let's say that you have an aneurysm that bursts. So you have a hemorrhage in your brain. So this is like a blood explosion in your brain here. And what would happen is you'd end up in the hospital, hopefully, get surgery right away. And then you would be placed on continuous EEG monitors, which are all over your head. and you'd be put in the intensive care unit. Now, those monitors are detecting for the possibility of seizure-like activity. Now, seizures are common. About 20% of critically ill patients get them. Seizures are very dangerous. They cause brain damage, they cause death. And doctors will do a lot to try to prevent you from getting seizures. They might even give you medication to shut part of your brain down to prevent you from getting a seizure that would destroy it. The seizures are even can be more damaging to your brain than the actual illness, the actual injury that caused this. Okay. Now, the only way to detect seizures and seizure-like activity is with EEG monitors, and that means that allocation of these monitors is really important because patients often tend to stay on the monitors for way too long, and that means the doctors aren't able to give the monitors to patients who need them. There's like a limited number of monitors and there's a limited number of people who can read the monitors, so they have to allocate the monitors carefully. So we really do need to predict seizures in advance so that we know who should be designated the monitors and when people can be taken off of the monitors. So I worked with neurologists to develop a risk score called 2 helps 2B that is now widely used in hospitals, and it's small enough that it can fit on a PowerPoint slide. But it's as powerful as our best black box machine learning models. So this is the 2 helps 2B score, and it's called 2 helps 2B because it's 2 HELPS and then 2 points for the B. So the doctors can memorize this whole model just by knowing its name. And then depending on the number of points the patient gets, that translates into a risk in this table at the bottom. Okay, so, and this predicts, like I said, this predicts seizures, and then that determines how doctors allocate these monitors, okay? So 2 helps 2B, as I mentioned, was not created by doctors. It is a full-blown machine learning model. It was created by data fed into an optimization problem. And I know it looks like a rule of thumb, but it's actually as accurate as black box machine learning models for our data set. Doctors can decide themselves whether they want to trust it. It's not like a black box where the doctor has to sort of decide whether or not to trust it. Here, the doctors, or the black box, sorry, let me say that again. So it's not like a black box where the doctors sort of have to trust it, right? Here, the doctors can look at it and they can say like, I'm not sure I agree with that set of points, right? I'm gonna adjust what I'm doing based on my own level of trust in this model. And then doctors can also calibrate the score with information not in the database. So if a patient has something special about them, the doctor can say, oh, that's worth like an extra point. And then also the score can be explained to non-physicians. So you can explain to someone's family member why they're being taken off EEG monitoring, for instance. Okay, now I know you're probably saying, well, but that only has 6 factors in it. That's very easy to construct. But the database that we constructed this from is actually pretty big. It actually has over 70 features, and the algorithm chose which 6 features to pick and how many points to give it, and the risk measurements as well. All right, so so far the 2 helps 2B score has been validated on an independent multi-center cohort. I wasn't involved in that study. That was done by neurologists. And this is what they found. So this is the predicted probability of seizure versus the true probability of seizure. So you want to be on this diagonal line here. And blue is the data that we built the model from. And then green is the validation data from different hospitals. And so as you can see, they lie kind of right on top of each other, which is really where we want to be, because that means it generalizes across institutions. And it's being used at several different universities or university hospitals. And so far, it's resulted in a substantial reduction in the duration of EEG monitoring per patient, which, according to the doctors, has allowed them to monitor 2.82 times more patients, which means that helps them substantially reduce brain damage and save lives. That's what they tell us. So that's been really helpful for them. All right, now the reason why we could do this, and it's a rare example of machine learning in a very high stakes setting, right? And And the reason we could do it is because it's interpretable, right? People could understand it. All right, now the second example I want to give is on power grid reliability. Now, my first job after I finished my postdoc, I took a real job, which was to work with the power company in New York City to rank all of the manholes in Manhattan in order of their probability to experience a manhole event, which is a fire or an explosion or a smoking manhole that's quite seriously smoking. Okay, so this is my actual first real job that I had. I did this job for 3 years in order to help the power company prioritize repairs. Now, these fires and explosions and smoking manholes, they can be really serious, and about 1% of the 53,000 manholes in Manhattan have some kind of serious manhole event each year, or at least they did when I was working on this. And most of these events are caused by breakdown of the insulation around the electrical cables that go through the manholes. And salt from the street that they put on in the winter is part of the problem with the insulation disintegrating. So the salt gets into the manholes and it disintegrates the electrical cables, and then there's a short circuit, and then they can have a pressure buildup, and that would cause an explosion. And so as you can see, there are many manholes on each street. Like this is from one of our visualization tools that we built, where we're coloring all of the manholes in service boxes by their vulnerability according to our model. Now, the data for this project was completely insane. It was like accounting data from all the way back to the 1800s. Some of these data were text documents. So like if someone's lights would go off, for instance, like the person would call up like a Con Edison dispatcher who would start typing in a trouble ticket for the event while they were directing the action of what to do about it. And I'm just going to show you, like, I just get a headache thinking about how difficult it was to analyze this data. My collaborator, who is an expert in natural language processing, she says this is not natural language. All right, so I'm just going to show you what this data is because it's just so unbelievable. So this is the front of the ticket. This is the back of the ticket. The front of the ticket has the borough, which is Manhattan, the house number, which is 135-6. So in some boroughs, this is a single house number, and in some of them, it's a range of house numbers. This is West 4th Street. This is an AC burnout. ACB is the code. And then here, this is the cross street. So it says here, CIB Powers, whoever that is, he reports that there's a contractor working in service box 158622 in front of 135 West 4th Street, has a 7-wire coppered at the west duct, and that means that an electrical cable has melted itself onto the duct connecting two manholes. So it says Manhattan District Engineer O'Hara dispatched, and then he arrives, and then he reports in this service box in front of 135 West 4th Street that have 7-wire main in trouble going out the west wall, unable to tell if it goes west or south in the crossing as per the MNS plate. So in other words, he's staring at like a little map of the mains and service plate, which is like a 3-block region of where the cables go. And he can't figure out where this particular cable he's looking at is going because it's melted onto the duct. And, you know, often these manholes are filled with just gunk, like mud and like whatever else you don't want to know. And so he can't see actually where this cable is going. And then it says here, flush required. So flush required means that they need to bring in a flush truck to stick a big tube down in the manhole and suck up all of that gunk, get it out of there so that he can go in there and work. So they ordered the flush, and then he reports flush truck still working in the trouble hole sometime later. And then finally he could get in, and he reports that he cut for replacement 340 DC cables. So these are old cables. And then 440 AC cables, and this is just the length of the cables, from this service box in front of our address to the service box in front of this other address. And then there's some parking information. And then he cleared the burnouts, and then he reports that the manhole needs a cut and rack, which means it's very messy, like the cables look like spaghetti, and he thinks that they should be aligned on the racks. This would be a lot of work, so he can't do that now. And then he's tying the neutrals in, and then he cleared everything and he's all done. Cleared all the burnouts and retied all the neutrals. So that's that's why this data was very difficult to work with. Anyway, so we did what any sensible machine learning researcher would try at the time. And keep in mind that this was before the term data science existed. So we thought we were doing machine learning, right? So anyway, we took all the data, we threw it into a black box, and we expected everything to work out. And of course, it did not. And in fact, all the machine learning methods performed the same and none performed well. Anyway, in the end, we picked ourselves up off the floor. We pulled out all the information from the trouble tickets. We did a tremendous amount of very difficult work and designed a model in which we understood every aspect. And it actually kind of worked. So I'm going to show you some results from a blind test in the Bronx where Con Edison engineers withheld data from our database. We had data only up until 2007, and then we were testing on 2007 data. Okay, so it was a completely blind test in the sense that we had no data from 2007 in our database. Okay, so what I'm showing you is the rank list of manholes in the Bronx. There were 27,212 manholes in the Bronx, and we're ranking them from most likely to explode to least likely to explode. And if there is an arrow labeled F, it means that that manhole had a fire in 2007. And if it's an X, it means explosion. Okay. So hopefully what you can see here is that our rank list is pretty good. Like a lot of the events that happened in the Bronx that year were ranked very highly. And what we found was that if Con Edison had inspected the top 10% of our ranked list, they could have prevented up to 44% of the manhole events that year. And there were some events that we didn't predict at all. And we went to look at the data to try to figure out why. And it turned out there was nothing in the data that would have allowed us to predict those events. Like these manholes over here, they had been inspected recently. They were clean. They were, recent new cables. So we didn't know why anything happened with those manholes. But in any case, we were really, really proud of the result on this test. And I fully realized that, frankly, it wasn't a more powerful machine learning method that was getting me better performance. It was really, an understanding of what was going on that allowed us to get to good test accuracy. So people often talk to me about the accuracy interpretability trade-off in machine learning. They often say things like, well, but if we use a more powerful model, we're going to get better performance. And this is a case in which the accuracy interpretability trade-off is completely reversed. Like here, interpretability led to more accuracy, and without it, we would not have been able to get it. So after this experience, that's when I started working in interpretable machine learning, because I said, I'm never doing this again. Like, I don't want to be in this situation again where I just throw a whole bunch of data into a black box and expect good performance, and I'm not going to get it. So, I want to be able to understand what is the science that I'm actually doing. All right, so I've talked a lot about tabular data, and I want to switch over to talking about raw data for a while. So raw data requires, as I mentioned, neural networks. That doesn't mean that they can't be interpretable. It's just that you have to figure out what interpretability actually means for these domains. So what actually is an interpretable neural network? So we gave it a try. We said, okay, let's give it a try. We'll try to construct one, and we'll do it for computer vision, because computer vision is the domain where the deep learning people really test their, that's where all the really amazing deep learning methods were sort of born, right? It was computer vision. So anyway, we designed a network that is constrained to make predictions in a certain way, okay? So it uses case-based reasoning, which is kind of like, I don't know if any of you have seen the television show Dr. House. or House it's called. But anyway, so Dr. House, he's this doctor, and he has all these patients who have very weird medical conditions. And he looks at them and he says, oh, that patient has a green toe. Well, I think it's, I've seen a patient like that before. That other patient had chilblains, so maybe this patient has chilblains too. Or like, oh, but this patient has a very particular heart condition. Well, that other patient had a similar heart condition, and that patient had blah, so maybe this patient has blah. So that's what we tried to do here. We tried to have the network reason about an image by comparing it to other images. And it has to do these comparisons and tell us exactly what it thinks of each comparison. And every step of this network can either be checked by a human, or it's adding up a bunch of numbers. Like it's like a weighted linear, a weighted combination of variables, okay? So what the network is doing is it says that it thinks this bird is a clay-colored sparrow because this part of the bird looks like this part of that bird. It thinks this part of the bird looks like this part of that bird. And this is a prototypical clay-colored sparrow, okay? So it's doing this comparison in the neural network's latent space. So it's saying, I think this looks like that. And the human can check it. The human can say, well, is the network right? Does this look like that? And that's why it's interpretable. It's because the human can check every piece of it here, every comparison. And the network says, well, I think this part of the bird looks like this part of that bird. And this is also a prototypical clay-colored sparrow. And I think this looks like that, and this looks like that. And all of these prototypes, by the way, are learned by the network. They're not given to the network by a human. They're actually learned by the network. And how to do these comparisons is all learned by the network as part of its training process, okay? So anyway, because the network because it says like this looks like that, and this looks like that, and this looks like that, we called the paper This Looks Like That. And what the technique does is it starts with your favorite black box, like you start with your favorite convolutional neural network, and then it adds an extra layer to it just before the last fully connected layer. And that forces the network to do this kind of case-based reasoning. So it forces the network to make comparisons and tell you what it's doing. And again, all the prototypes are learned during training. We usually use 20 prototypes for each class, but that's a parameter that you can adjust. Okay, so again, you take your favorite convolutional neural network, and then you transform it to be interpretable by adding this extra layer to it that forces these comparisons to be made, okay? And there's 20 comparisons per class. All right, and so the network scans the image, scans whatever the input image is. It scans it looking for parts of the image that it thinks looks like the prototypes. So let me show you more detail about this whole calculation. I'm going to run through the full calculation from this whole part of the network on the next slide for a couple of different classes. Okay, so why is this bird classified as a red-bellied woodpecker? Okay, so the network says, well, I think this part of the bird looks like this part of that bird. And it's going to give it two numbers for that comparison. One number is for how similar it thinks this looks to that. And that number is 6.499. This is a really high number, by the way. So what the network is saying is like, I really think this looks like that. And a human can come in and say like, yeah, that is quite similar. I mean, these birds have red heads. They have like a little black here. It's like white over here. Like it's so similar. I'm going to give it a lot of points. And then it also has this number over here, which tells you how important this prototype is for this class. So how representative, how prototypical is this bird to the red-bellied woodpecker class, okay? And it does this for all 20 prototypes for this class. And so here it's comparing the pattern on the feathers to the pattern on this bird's feathers. And it's saying, that's pretty similar too. And this bird is fairly prototypical, right? It's got this nice score for this bird, okay? And so it keeps going like that. And then it does it, like I said, there's 20 numbers that get multiplied together, or 40 numbers, I guess, that get, these numbers get multiplied together and then added up, and this is 20 numbers you add up. And then this is the total number of points for this class, okay? And it does this for all the different classes. So for instance, here's the next highest class, which is the red-cocketed woodpecker class. And so the network is trying to gather evidence to say, like, why is this a red-cocketed woodpecker? And it says, well, I think these feathers look like those feathers in this bird. But you see, the thing is, apparently red-cocketed woodpeckers don't seem to have red heads. And so it can't really seem to get the points that it could get from the other class by the comparison of the red heads. And so it just doesn't get as many points. And it doesn't always do things correctly. Like, it sometimes gets predictions wrong. So here's a case, for instance, where it messed up. And it classified this bird as a prothonotary warbler instead of a Wilson's warbler. So here are the Wilson's warblers. Here are the prothonotary warblers. And like, I don't know about you guys, but when I'm looking at this, like, that bird to me looks like a prothonotary warbler. It's just, you know, I can understand why it made a mistake. And as I mentioned, you can transform any black box model convolutional neural network to be one of these proto-PNETs. And so here we used a DenseNet 161. If we switch that out to a VGG16, it actually gets it right. And then we can kind of figure out what happened here. So if you take a look at this bird, it's really doing a comparison on like the eyes and the beak, right? That's what information it's using. But what's interesting is that it's completely avoiding comparing the head, because apparently Wilson's warblers have these big black spots on the top of their heads, and this bird does not. So what I think is going on is that this bird might be like a baby Wilson's warbler, and because of that, it might have looked like more like a prothonotary warbler. Okay, so we've been comparing the accuracy of our methods, you know, the neural networks that are made to be interpretable. We're comparing those to the black boxes on benchmark computer vision data sets. So these are the data sets where people test deep neural networks against each other. Right? These are really benchmark data sets. Okay, 200 classes of birds. The original black box accuracy is between these values. If we transform all those networks to be interpretable, we get accuracies within the same range. And then if we stack all the interpretable networks together, then we get an accuracy that's actually better than any of the individual ones. And it still yields an interpretable model because it's still using this case-based reasoning. Like, humans can still check every, you know, it can do that visual comparison to see whether this looks like that. And it's also adding up, and the rest of it's just linear, right? So what I'm saying is that even for computer vision, we can have an interpretable model of the same accuracy as a black box, right? I have yet to find a domain where I actually need a black box. And we're in the process of applying this to mammography, which is obviously the kind of the ultimate in computer vision challenges. And we have some good preliminary results, and we actually have a recent paper on that too. In any case, I want to switch topics a little bit. As I've already spoken to you about, an interpretable model is when you do not use a black box, okay? Whereas an explainable machine learning model, or the field of explainable machine learning, is about when you use the black box and then try to explain it afterwards, like post hoc. So explainable machine learning became really popular about 5 years ago, and people are really, really enthusiastic about this idea of explaining black boxes. So in explainable machine learning, you start with a black box, and then you either create another model that approximates it, you compute derivatives of it, or you visualize what part of the input the model is paying attention to, or you do you make any number of other excuses as to why it's okay to have a black box. And there is this real divide, you know, of people who want to explain black boxes, and the growing but small number of people who are like, no, we don't need the black boxes. So I, of course, am on this side. I'm okay with you explaining black boxes if it's not for a high stakes decision. Like, I don't care, whatever. If it's not high stakes, it doesn't matter if you get it wrong. But if you're working on a high stakes decision, you really shouldn't be explaining a black box. And why not? It's because, you know, well, as I showed you, I don't see a reason why we need black box models in the first place. Like for every domain where a black box is performing well, we've always been able to construct an interpretable model of the same level of accuracy. And also, all these explanation methods, they just lend authority to the black box. And they're also often flawed. They're also, they try to explain what's going on, but they do it wrong. So I want to, a key motivation for this explainable machine learning is this accuracy interpretability trade-off that I mentioned earlier. So this particular figure that I've shown you is supposed to illustrate accuracy interpretability trade-off, okay? So I have performance on one axis and explanation effectiveness on the other axis. And this is from the DARPA Explainable AI BAA, and I looked at this figure and I thought, what in the world is this? Like, this doesn't correspond to any real problem. These axes are not quantified. These dots don't look like they were even plotted. They look like they were like drawn like Trump with a Sharpie or something like that. It's just sort of, somebody made this up. And then I thought, well, what are they doing? Like, are they using a static data set and a fixed evaluation metric? Because that's not how we do things in data science. Like, as I told you with the Power Grid Reliability Project, that's not how we do things, right? In a typical knowledge discovery process, we're supposed to interpret the results and use that information to inform our data processing. So we don't use static data sets, and we usually revise our performance metrics. So this is just not reflecting that. But even if you did use a static data set, then the trade-off doesn't happen like this. So even with computer vision, as I mentioned, you can get something that's very effective in terms of its explanations and still have the learning performance of the same level as the black boxes. And then it wasn't even talking about whether they were explaining black boxes or designing inherently interpretable models. Like, they didn't even say what they were doing there. So in any case, I have issues with this figure. I just don't think there's any scientific evidence for an accuracy interpretability trade-off at this point. Okay, so, I want to point out that approximations are not explanations. So a lot of people say, oh, well, I don't need an interpretable model because I can explain my black box. And then they create an approximation to the black box, okay, that is approximately equal to the black box. But the thing is that these are approximations and not explanations. The black box and the explanation could use totally different variables. Like, if there are correlated variables, the black box could use one of them, and then the approximation could use the other one. So it is entirely possible that somebody could create an explanation model for criminal justice decisions that, or like predicting recidivism, that depends on age, number of priors, and race. Whereas the black box only depends on age and number of prior crimes. And so someone might actually do this and take an approximation to the black box, see that it depends on race, and then conclude that the black box also depends on race in a way that's not through age and criminal history. And you could say that this would never happen, right? This is silly. Who would make this mistake? But it actually might happen, and it actually did happen. And it happened with COMPAS. It happened in the famous ProPublica article that a lot of people talk about. This is exactly the mistake that they made. They approximated COMPAS with a linear model. The linear model depended on race, and they concluded that COMPAS depends on race when it may not. Okay, so just to give you some more details here. So ProPublica showed that the false positive rates and false negative rates of COMPAS varied by race. And then they suggested that that might not be a good comparison because the people in the database, the blacks and the whites in the database, have completely different demographics. Okay, so they suggested that might not be a good comparison. We should include age and number of priors and re-examine. Okay, now the reason why you do this is because race is correlated with these factors because of systemic racism in society. That doesn't mean that that's embedded in the model, right? This is in society. Systemic racism is causing this correlation, okay? So after including age and number of priors, they still found a linear approximation to compass with a low p-value for the race covariate. So they said, okay, well, then this model depends on race in addition to age and criminal history. Okay, so they concluded then that compass depends on race. But I don't think compass is linear, and so I don't think their conclusions actually follow. So I'm going to show you why ProPublica's assumption was particularly bad. Okay, so took the data from Florida that was used in the ProPublica piece, so it's the same compass data that I was talking about earlier, and I plotted it. And this is compass as a function of age, and each dot here is a person. It's their compass score as a function of age. And what you should hopefully be able to see is that there's a fairly sharp cutoff here. I mean, like if you're 20 years old, you're not going to get a -4.5 compass score, right? And so hopefully you can see that. I mean, there's a few outliers here, but we think that this might be the contribution of age to compass. And it looks like compass depends heavily on age, okay? And so if they messed up age, this could definitely mess up their analysis, right? Compass does not seem to be linearly depending on age in any way that you could really see it, okay? So in any case, we decided that we would take away this function of age, okay, just subtract it off compass and see if the rest depended on race, okay? So we said, okay, so if we take this nonlinear function of age out of this thing, do we still get a similar result to like ProPublica that compass would depend on race? Okay. And it doesn't seem to, because we tried machine learning models with and without race to see if they need race to predict compass well, and they perform similarly. So we don't really need race to predict compass well. So race just doesn't boost performance here. And so ProPublica's conclusion is pretty shaky. So if race doesn't actually appear in compass other than through its correlation with age and criminal history, then how did they find these pairs of people? Like, so the whole article, they had tons of these like graphics with pairs of people. It's like a black person and a white person, where the white person has this really long criminal history and a low compass score, and the black person has just a couple of misdemeanors or something, and they have this really high compass score. Like, how is that possible? The thing is, if you look at these two people, the black person is much younger than the white person, okay? So like that could, if compass depends heavily on age, that could explain how this happened, right? Vernon Prater is old, so he doesn't get the age points. And I'm not saying that I agree with this, right? I'm not saying that that's the way age should be used in these models, but if they had compared two people of the same age, then it would be a lot more convincing that compass depends on race in addition to the strong dependence on age. Anyway, so ProPublica's claims not really holding up with respect to race. Compass might not actually depend on race. But I think there's a much worse problem with compass that ProPublica completely missed, which is that humans are not very good at inputting data reliably, which is what caused the issue with Glenn Rodriguez. If you have 137 factors entered by hand for each survey, if you have even a 1% error rate, there's a 75% chance of at least one typo in a survey. This, of course, is a huge disadvantage to complicated or proprietary models. And like I said, it's exactly what happened with Glenn Rodriguez. And so we were looking at the Florida data to try to figure out like how often these typos might happen. And we found some pretty strange inconsistencies in the data. So here, for instance, are people who got the lowest possible compass violence score. Like its compass is 1 through 10. And this is the lowest score you can get. And these people all have like multiple prior arrests and charges. Here are some of the prior charges that they've had, like things like attempted robbery with a deadly weapon, and carrying a concealed firearm, restricting obstruct officer with violence. It's just not clear how this could lead to the lowest possible compass violence decile score. It just doesn't make any sense unless there's some kind of data issue. And that's just the tip of the iceberg. There was a whole bunch of people with compass scores of 2 and 3 that all had this same thing where it's like, kidnapping and, it doesn't warrant a low compass score. It doesn't seem right. Anyway, we even think we found possible typos in the Compass documentation from the company that makes it. Like, they claim it's a linear function of age. And as I showed you, we don't think it's a linear function of age. So anyway, we wrote an article attacking both ProPublica for explaining a black box wrong and Compass for being a black box where typos can cause decisions. And the editor of the article, the famous statistician Zhaoli Meng, solicited a whole bunch of commentaries on our article by famous criminologists. And he also got an article by the makers of Compass. And they wrote a scathing article saying, that Compass is interpretable, which is pretty funny because if that were true, it would have saved me and ProPublica a whole lot of trouble. But in the mountain of criticism there, they admitted a couple of things that were super interesting. Like, they wrote that we have taken a clearly informal description of the violence score in the practitioner's guide. I showed you that formula. It was an equation. So I don't know how much more formal you can get than an equation. But anyway, they wrote it wasn't intended to be a technical document. So why did you put an equation in it? But anyway, so they wrote discussions of appropriate transformations are beyond its scope. And we note that the skewed age variable is an ideal candidate for a normalizing transformation. We thought, oh, wow, my goodness. Okay, and then also, in terms of transparency, they wrote that they're trying to pursue copyrights to make these scores publicly available. And I was like, whoa. Anyway, so I finally got sick of people trying to explain black box models. So I wrote this article saying, could you please stop? I wrote it, the original title was Please Stop Explaining Black Box Machine Learning Models for High Stakes Decisions and Use Interpretable Models instead. But the editor made me take out the please. So that made it sound more commanding. It's like, stop doing this. And I gave a lot of reasons. So the first one being there's really no scientific evidence for a general trade-off between accuracy and interpretability. Even for deep learning models and computer vision, interpretable models can be built at the same accuracy as a black box deep neural network. And for tabular data, most machine learning methods are equally accurate, including sparse models. And so explaining a black box then gives it unnecessary authority. All right, thank you very much.
Thank you so much, Cynthia. That was an incredibly illuminating talk, and I've already received a lot of questions from the audience that I'll try to forward to you. Let me just set that up a little bit. We can start with one that I'll just forward from the chat, basically. So, can you say something about what led to the deeper understanding in the manhole event example? You said that we have to understand the data, we have to understand the model, but what about it? What was it that led to this increased understanding?
So we actually pulled out information from those text documents that I showed you and put them into like a structured database. And we combined that with the cable data that was very, very cleaned up. We had to do a lot of cleaning on the cable data, because if we just do a regular, just try to figure out which cables go into which manholes, if we do a regular join, we'll lose half the cables in Manhattan. So we were just really careful at like cleaning the data and like pulling out the information from these text documents and associating them with the proper manholes. And then from there, we built very simple machine learning models, like, take the number of cables that were put in there before 1930 and like multiply that by 2, add the number of like aluminum cable, it's just it was a linear model. It's very, very simple. And those were the models that we ended up kind of giving them as our ranking models.
I see.
Those models worked very nicely, to be honest, because it was so clean. The data was so clean. And we also built we built a piece of code that we called the report card code, because it gave each manhole a report card. And it talked about like, okay, this manhole, here are all the cables in the manhole. Here's when they were put in. This is what the inspection reports say. Here's some important information from those. And so we'd go through everything you need to know to assess how vulnerable that manhole was. I could give multiple talks about just that project.
I'm sure you could. Thanks a lot for elaborating on that. We have a question from Simon Olsson. I'll ask him to ask it himself. So you can go ahead and unmute yourself. There we go.
Yes, thank you, Cynthia, for a very interesting talk. I could recognize a lot of the sort of case studies from a ethics lecture I gave in an introduction to data science course yesterday. So it seems like it's due for revision now after your. But I have a general comment or a question to you, sort of. So you alluded a bit to that the data in general that is used for this sort of this future offense predictions or social outcomes, it tends to be entrenched in biases, and there's a lot of data errors. Sort of the reporting of the data is errors. So to what extent do you think, as data scientists and machine learning people, should be engaged in the task at all of predicting social outcomes? Like the examples that you showed for prediction of reoffense had a pretty low accuracy overall, even in the interpretable model, and to me, this is very alarming that we are relying on sort of this quote unquote objectification of a truth in a sort of a formal terms of just justifying making a decision. So your comments are very much appreciated on this.
Yeah, that's a really good point, and there's a lot of debate about this. So I think it's not really about what you're predicting, it's about what you do with those predictions. So for instance, Minority Report is the example everybody always brings up, like the movie Minority Report, where they're predicting future crime and then they punish people for a crime they haven't committed yet, right? So, so I think, there's a very big difference between what people are doing in the criminal justice system and Minority Report, okay? So let's say we take these predictive models and let's think about all the different things you could do with them. So one thing you could do is you could use it for sentencing. Also, you could use it for bail. You could use it for parole. So sentencing is tricky. I actually don't think we should use them for sentencing because I think you should be sentenced for the crime that you committed, not the crime that you will commit. Okay, just like that. But in terms of bail, there's a matter of public safety. If somebody has a long criminal history, you don't want to give them bail, right? Because then they're going to go out and while they're in bail, they're going to commit a crime. So, and then the thing is, the alternative to these machine learning models are judges. And judges are biased black boxes, unquestionably, right? We know that. We've done many studies on that. We know that that's true. So, you have these machine learning models that can take these data from these large databases and at least find patterns in them that can help you. Like people with longer criminal histories should be should be less likely to get granted bail. Okay, and if we kind of at least make that make it so that's clear, then you don't have the judge staring at the person, looking at their race and making a decision that way. So it's really tricky because you also, and then the question is, well, should we use race? Well, okay, let's think about what else we could use these models for. Let's say we're allocating social services. Should we maybe think about these people, should we maybe use race in helping to allocate social services to the people who need it more, right? Maybe we should be using race in that case. So these questions, I think, are very, very application specific, and that you can't talk in general about should we make these kinds of predictions, because I think the answer is in some cases, or in many cases, yes, we should. But should we use it for all different applications? No, we should not. I hope that answers the question.
All right, thank you so much. I would also like to remind the room over in the Chalmers courthouse that you can ask questions there. The only thing is I can't see if you want to ask a question. So Kolbjørn, maybe you can figure out, maybe you can stand in front of the camera or something like that if there's a question that somebody wants to ask. Oh, you're already standing. Great. We'll move over to our live audience then at the courthouse. Kolbjørn.
There's a bunch of really good questions in the chat. I wouldn't mind answering some of those.
We can do those. We can do this first then. So two questions in the chat relate to your prototype CNN model, I would say. DevDat asked, for example, are the prototypes selected manually or can they be learned end to end? And somebody else asked, do you lose sort of efficiency, or do you have to do more computational work in computing these kinds of models, or computing with these models? I think those kind of go together a little bit. You could answer those together.
Yeah, so the prototypes are learned, as I mentioned. They're chosen by the algorithm during training. The process for doing that is computationally intensive. So what each prototype is, it's an image that's projected into latent space. It's one of the training images that's projected into latent space. And so typically what we would do is to search through the latent space for prototypes. This is all gradient descent, so you're sort of moving around the latent space. And then every once in a while, we snap the prototypes to an actual training point that's been projected into latent space, so that each prototype actually does correspond to an actual image from the training set. And then we sort of, release it, and then again, prototypes go wandering around in latent space, not necessarily corresponding to an image, and then we snap it back. So it's the sort of, we have these projection steps throughout the training process. And is it more difficult to train? Yes, it is. And for example, so going back to tabular data for a minute, so yes, the interpretable neural networks are harder to train. They can be trained. We have many students who've done it, and not just at Duke. So there are hundreds of papers now that have extended that particular work, to different applications. So other people have done it too, and people have also kind of extended it to ways that are easier to train. The way I like to say it is that we've had gradient descent kind of working on regular neural networks for years, but for our interpretable networks, we only had a couple of years of Duke graduate students training them. So now it's like more people doing it, and it's easier.
Yeah.
In terms of,
can I just connect on that question? We had another one in the chat, which was, or that point rather. Somebody else asked, do you think it takes longer to develop these things? I guess you already answered that to some extent. You've only had a few years to do it, but yeah, more in general, do you think it requires more effort to do this? I mean, in some sense, it has to be tied to the application, and
Yeah, it's tied to the application. It's tied to the constraints. If you have more difficult constraints to satisfy, it's harder to get them incorporated into the models. No question. Going back to tabular data, if you think about how easy it is to train a logistic regression model, okay, that's just convex optimization, easy. But if you're trying to train the 2 helps 2B score, well, that is a mixed integer nonlinear program, right? It's much harder to solve because you have to get, a sparse model with integer coefficients. And so computationally, it's just much, much harder.
Yeah. I'm going to let somebody in from the participant list who have their hand up. So Matthias Wade, would you like to ask your question? I think maybe I have to unmute you, actually. There we go. Matthias, are you with us?
Yes, I am now. Sorry, I couldn't unmute until now. Hello, Cynthia. Thank you for this very nice talk. I'm working with interpretable approaches to conversational AI specifically, a subfield where whereas I'm sure it's completely dominated by black box approaches, and with all the associated drawbacks like lack of transparency and occasional catastrophic failures and things like that. So my question is, or rather, I'd like to hear your opinion on the importance of interpretability in conversational AI specifically.
Yeah, okay, so that's a really good question. And I have a former student who went to do a PhD in natural language processing over at UNC. And I have this ongoing debate with him as to whether or not interpretability is actually useful for anything involving like natural language. And I claim that interpretability is not really needed for natural language, and he thinks it really is needed. Like, he actually works in NLP on interpretability with these other people, like because he and I also disagree on this. So I think natural language is already interpretable, and so and these aren't really high stakes decisions, in the vast majority of the time. So it doesn't seem to me that it's really worthwhile to try to embed interpretability into it unless you really need to troubleshoot it to the point where you can't just augment the data in a way that it's clear that where it's misbehaving. So I guess my argument is that you don't. My argument why you don't need interpretability for that domain is because natural language is designed to be understandable to other humans, and so
right, but
it's already got it.
Right,
yeah.
But if I may follow up just with one example, there is the huge conversational system called GPT-3, which that's an example of a black box, right? And it was tested in a case where researchers were posing as psychiatric patients and asking talking to this network. And at one point, the researcher said, okay, I'm feeling really down, maybe I should commit suicide. And then the network says, yes, I think you should. which of course is a disaster, right? So that's what I mean with, in my opinion, where you need interpretability also in conversational AI, because there may be high stakes decisions. For example, you may use conversational AI for helping psychiatric patients, as an example.
But why would you, if you had a patient who is potentially suicidal, wouldn't you refer that to a human psychiatrist?
Probably yes, but the argument that was, I wasn't involved in this paper, the argument was that it was somehow beneficial for these patients to have access 24/7 to this type of interactive system, which they wouldn't have with their doctor.
But that system, it's better not to have access to it.
Yeah, most likely, yeah, I agree. But that's
the
because it's a
few hours
black
of the
box, right?
Yeah.
To a great extent.
Well, not just because it's, well, you're right. Okay, yeah, it's because it's a black box. So yeah, I mean, I've been battling GPT-2 a lot because I run the Duke poetry team, computational poetry team. So we have a paper on like limericks, and basically the whole paper was just battling GPT-2 to get it to like do something reasonable. Yeah, I don't know what to say about those language models because I don't work in NLP, and so I just don't know how to make those things interpretable.
Okay, thanks.
Yeah, sorry.
Thanks.
All right, thanks, Matthias. So you touched on something there, Matthias, in your question, which was this is a high stake situation. We need interpretability and so on. And Cynthia, you drew a distinction, or maybe not a distinction, but you mentioned the fact that interpretability is extra needed in high stakes decisions. Should we actually make that distinction? And if so, what is a high stake decision? Are there examples of problems where you wouldn't want this kind of model?
Yeah, it's all very domain dependent, right? So for example, with computational or online advertising, right? Where did machine learning grow up? It grew up predicting, predicting which advertisement you're going to click on, which Facebook, whatever article you're going to read, which news article you're going to read on Yahoo, right? All those decisions are like low stakes. If I feed you the wrong news article, like who cares? You don't like that article. Maybe even it's a discriminatory article and you feel offended. That's still not that high stakes. You know what I mean? It's not like you get denied a loan where the loan determines whether you can buy a house, right? So, I think it's just really whether or not something is high stakes very much depends on the domain.
Yeah. No, I mean, I completely agree with you. I think if I took anything away from your talk, though, is that there isn't a trade-off between interpretability and accuracy. So why not use them all the time? The interpretable
Well, again,
models.
it's because they're harder to develop, right?
That's a good point. Yeah.
So if you just don't care, if you just don't have the resources to develop a model that's interpretable, and some people don't want interpretability because then it jeopardizes their proprietary information from their company. Like if Compass released their actual formula, I'm sure it would be like this, like, whatever they put in their practitioner's guide could be like this big. But they don't want to release that formula. So it's better maybe if it's kind of a black box.
Yeah. I forgot to mention, by the way, this was a question from Anna Bakido in the chat that I forwarded. We now have Alexander Sampson, who has his hand up. I'm going to find you and unmute.
Hi, thank you so much for the talk. I guess in the Matthias case, when the stakes could be high in natural language processing, for example, you would say that interpretability shouldn't be like that demanded, right? How about the explainability? Would that be the case?
Oh, sorry. So the question is, if you were in a high stakes setting with a black box?
Yeah.
Sorry.
So you would you argue for interpretability, right?
Yeah.
But explainability is kind of like a different thing, I guess, right?
Yeah.
And in this scenario, maybe like to debug the model, you want it to be explainable. Is it actually do you draw the distinction between those two when you say that you don't need interpretability for NLP tasks?
Well, I think if you want to debug it really well, it might be helpful if it's interpretable. But there are ways to debug big models without actually needing to embed interpretability constraints into them. Like sometimes you realize, oh, it's just not performing well in this domain. I'm going to add a whole bunch of extra data in that domain and I can just get it to perform well. So, it just really depends on the actual problem that you're working on, how easy it is for you to debug it. Like for some researchers, trying to create an interpretable model would be very difficult because they don't know how to do it. They don't know how to train machine learning models that well. So it's better off if they get somebody else's code and they don't mess with it. And instead they just augment the data set, right? Just add more data and then just retrain using the code that they already know kind of works, right? That's the level that most AI researchers are kind of at, right? Who are doing machine learning, right? Because it's exploded fairly recently, so you don't have people with a tremendous amount of training. Oh, I can't hear you.
Are you asking a follow-up, Alexander?
Might want to go off mute.
Yeah, there we go.
Yeah, I muted myself because the place could be a bit noisy. But I guess like they develop kind of the systems like BlenderBot 2 with like sort of safe conversation that you can have with the transformers of some sorts. So yeah, but another one could be that when you show this system that is interpretable, the network that distinguishes between birds, right? Would this, do you have like a sort of a benchmark for interpretability, or would you argue that you don't need any benchmark for interpretable AI? Because in explainable AI, in different methods that they currently have, they try to develop currently the benchmark how to evaluate the explainable strategies or explainable methods. Would you argue that you need the same ones for interpretable AI?
Yeah, so the question is like how to define interpretability, and it's not clear. It's all domain dependent. So a lot of the work that I'm doing in my lab is measuring like sparsity as a proxy for interpretability. You know, not all sparse models would be useful in a particular domain, but you know, because humans can handle a limited number of cognitive entities at once, sparsity is a good proxy for interpretability. It's at least necessary for interpretability, right? And then for the birds, what we did was impose a set of constraints on the model so that every calculation could be either checked or it's a linear model. And you know, that's how we defined interpretability. It was like that's how we defined it. And you know, I think at this point there's room for a lot of creativity in the definition of what is interpretable, because humans understand things in different ways, and they do that in different domains as well. You know, I think human studies are there's a lot of people who do like human studies to show like whether a model is interpretable or explainable, but human studies are so challenging and so error prone that I generally try to avoid them if I can possibly help it.
All right, thank you so much, Cynthia and Alexander. We've had a few questions asking about whether interpretable models are heavier to compute with generally, or less heavy, and so on. And maybe you can elaborate on what stages of computing with these models are heavy or less heavy compared to black box models.
Okay, so they generally are much heavier in terms of the training, but lighter in terms of the testing. So for instance, with the corals model that I showed you, a human can just compute the model in their head, right, once it's trained. But training that model, that's an NP-hard problem. It's factorial in the number of features. And so our method for training, you know, corals and optimal sparse decision trees right now is like a branch and bound algorithm. Right now we're using like dynamic programming with bounds so that we can lop off parts of the search space. And this is, you know, we have our own like special bit vector libraries to help us do this faster. It's very, very sophisticated code to make the things run faster. You know, if you just did it with a naive implementation, you would be at least 4 orders of magnitude slower than we are right now.
Yeah, and I mean, related to this question, I think maybe I can forward Robert Feld's question here from the chat. So he's saying that our experience is that scalability can be hampered, i.e. if you have a truly large problem, for example, many columns in tabular data. So this is something that, for example, in a rule-based system, like you talked about before, these risk scores, you end up with a huge set of possible candidate rules that you could include in your score. So thinking ahead, or even evaluating the situation right now, how do you look at this problem? How do we come up with models that work in this setting?
Welcome to my life, right? So, okay, one good thing is that most real-world data sets for like that are high-stakes decisions are not that big. So, like the hospital data set, there's only a certain number of patients that are critically ill every year, you know. So, like, you don't have these massive data sets. But even for data sets like, so let's think about like the FICO data set for the Explainable Machine Learning Challenge, right? So that's a benchmark data set given to entrance into this competition as a benchmark data set. They told us create a black box and explain it, okay? So we took this data set, 10,000 loan applicants, half of them denied, you know, half of them default on the loan, half of them don't. What do you do with it? And what we did was we created 10 little itty bitty additive logistic regression models and combined them together in a logistic regression model that was 10 terms, okay? And that thing performed as well as the best neural network. So sometimes you can decompose these problems and create like sparser models on the subproblems so that you can take that bigger problem and decompose it into smaller problems that you can actually solve. You know, I spend every day thinking about some aspect of how do you scale sparse models to larger data sets. And like, for example, we just had a paper accepted to AAAI on massive improvements in scaling in decision trees. Like, this is like the latest of the chain that the Corals algorithm was part of. So I'm just gonna put that link in there, and so you can kind of see like what works, what we're trying to do to try to improve the scalability of these problems.
What's the sort of one-line summary, if I may ask for a trailer or a teaser?
It uses the accuracy of the black box on subsets of data to serve as like a benchmark for the sparse decision trees. It tries to match the accuracy of the black box on each subset of data. And if it can do that, then it's happy. And by using the black box as a reference model, it saves us a lot of computation.
All right, let's see. So you two asked the question in the chat. Would you like to forward the question yourself? Maybe I should have asked this before. You're still around, so I can ask to unmute. You can choose to or not.
Hi, thanks for the talk. I'm a huge fan of your work. You mentioned earlier that about recommendation engine for ads, and those are usually based on black box models. And one of the approaches that the internet companies took to understand those models is to run like online experiments, like A/B testing on those models. Do you see other domains where such a method can be applied to explain black box models?
To explain black box models?
Yeah, in the sense that you just change like a small difference, make a small difference in the model, and then you introduce the alternative model to the application to the problem, and then you want to see if, yeah, I don't know.
Yeah, there's a whole bunch of models, a whole bunch of methods that basically are sensitivity methods to explain black box models. I thought you were going to ask a different question that I thought was really interesting. Actually, I thought you were going to hit on, you know, can we use interaction between the user and the model to design a more, you know, a better interpretable model. And I think that's where the next frontier of machine learning will be, is like trying to combine human knowledge with the machine learning to design better models.
All right, Cynthia, we've kept you for a long time. I'm going to try to wrap up, but we have a few more questions in the chat. Do you have a few more minutes?
Yeah, of course. There was a couple earlier ones that I didn't get to,
sure.
but they're really good.
Yeah, feel free to get to those.
Can I pick this one over here?
Yeah, pick one.
It's one of the first ones. So it says, with tabular data, would you recommend people first explore simple machine learning models before throwing complex neural networks at it? And actually, I have a really different, you're not going to be expecting this answer. So because black box models are fairly easy to train, What I recommend doing is trying to use a lot of different machine learning algorithms. So in other words, throw a neural network at it, throw boosted decision trees at it, throw random forests at it, because those are all pretty easy to train, right? And I would also throw logistic regression at it. And if they all perform about the same, then what it probably means is that the data set has what I call a large Rashomon set, which means that there are a lot of models that perform well. And then in that case, I claim that that those are cases where you can happily look for a simpler model that will achieve the same level of accuracy as the black boxes. So it's like a nice way to check before doing any really hard computation whether or not a simple model is likely to exist at the really sparse models likely to exist.
All right, thank you for that. Joachim and Dian, you've been waiting patiently for me to ask you a question. Would you like to ask it yourself?
Yeah, sure. Thank you for a great talk. This was really interesting. About this, the prototype network that you're presenting, there's still some, I guess, black boxes there in terms of how it's determining the similarity between the patches and so on. Do you think this is something that needs to be explored further, or are we kind of happy with the fact that we can verify that it seems to be able to match these things up, and we don't really need to go into any deeper there? I don't know.
Well, I think that as long as a human can verify it, then that's at least better than where we were before. There are a lot of deep learning methods for high stakes decisions in healthcare that don't require interpretability. So for instance, there was a lovely method created by a company, I can't remember, I think it was called Arterus, I don't know. But they were trying to segment the chambers of the heart automatically, okay? So it would take an image of a heart, and then the doctor normally would have to put points all around the outside of the chambers. And this method would just put those little points on there, and if it was wrong, the doctor would just fix it, just move the little points back. And so it just saved the doctor time. And we don't really need to know exactly how it worked or what it did. We just need to know that it put the points around the chambers of the heart. So like, it gets to be, it gets to be that there's some problems where, as long as a human can visually verify it or visually decide whether they agree with it, then that's good enough, right? I'm not claiming that the model that I produced is the best thing ever. Like, I know there's people who've extended it, who've done even much better work than we have on extending it to other domains and making it easier to compute. But it's at least a method that proves that you can get interpretability, you can add a lot of interpretability constraints without losing accuracy.
Right. I guess the issue comes in once you put these things into automation and there is no human in the loop, then you might need something that you can maybe, I guess I'm sort of equating interpretability with trust, which is maybe a mistake. In this case, you're able to interpret it because you can audit it, but that doesn't mean that you can trust it to go and do its thing reliably when nobody's watching. I guess those are different things.
They are different things, but I find interpretability is a necessary component for trust. So for instance, let's say that you put a model in a self-driving car, it doesn't really work, okay? A car crashes into a person or something like that, okay? So then you want to be able to go figure out what happened. Like, why did it do that? And it would be really helpful if it was interpretable, right? Doesn't mean you can trust it, but at least interpretability tells you what happened there.
Right.
All right,
Great,
thank you, Joachim, and thank you, Cynthia, for that. So we had another one earlier in the chat here from Kreske Ecke, who asked, you mentioned the term giving black box models authority a couple of times. Could you please explain a little bit more what you mean by authority in this context?
So, I mean, when this explainability wave started, like, I've been working on interpretability for years, and people would say to me, I don't need to be interpretable. I can explain the black box. I know exactly what it's doing. I don't need an interpretable model. And basically what they were doing was making excuses for why it was okay to use the black box model. So it was giving the black box an authority, despite the fact that, these explanations are flawed, often wrong, and they contribute to using a model that's more complex or more black boxy than you need to be.
All right, we're going to wrap up with the last one. I wrote a few moments ago that we had our last question posted. So I'm going to ask Newton, do you want to ask your question yourself? Let's see. Yes.
Oh boy.
My question is that it's a bit of an argument against why you will not want to have interpretable models in some areas which are not considered high stakes. But if you think about it from a more theoretical angle, ethical theoretical angle, you could say that all humans have the right to make informed decisions in order to give consent for using ML technologies, and interpretability gives you the informed ability, the ability to make the informed decisions. What will be your thoughts about this? So this is despite the stakes. You want to have interpretability across all sectors without considering if they're high stakes or not. You just want to make sure that you enable people to have the ability to make informed decisions.
Well, I mean, I don't really know what to say about that because it's so general that it doesn't, it's not clear what domain that it's talking about. So I don't really know what to say about that because it's not a specific domain. Like for instance, like I said, I'm talking specifically about machine learning models, which are predictive models trained from data sets. Those data sets are almost always flawed. And we're trying to use those predictions to help make decisions. And I'm just working in that very specific case. And like there are even, like I said, distinction between very related questions where one you need interpretability and one you don't. Like for instance, with mammography, you would need interpretability to look at an image of a breast lesion and try to figure out whether to give the person a biopsy. Whereas you don't need an interpretable model to figure out whether there's any lesions at all in the image, right? Because the explanation would be, I can't find any lesions, right? There's no lesions in this image. So, I'm not sure what to say about the abstract ethical argument. Yeah. This is something that maybe we could have a very long conversation about, and maybe you could explain it to me, but I don't really understand.
Let's try to set that up. For sure. I'm going to break with what I said just before, because we've got one more question, and I'm very interested in causality myself. Leif asks, how do you view the relationship between interpretable models and causal models?
So I think there are some cases where causality is a necessary component for interpretability. There are some people who will not consider a model interpretable unless it is causal. I don't think that that's necessarily needed for all cases. For example, I don't need to know why I predicted that you'll click on this advertisement. I don't need to know what was the cause of the reason that you committed so many crimes in the past. I just need to know that the fact that you committed all those crimes in the past is likely to help predict that you might commit a crime in the future. So I think it just depends on the domain whether causality isn't a necessary component for interpretability.
So let's make it a bit more specific, because you have the risk scores, for example, right? So you have a number of clinical features, for example, or demographic or whatever it might be. Some of those features could be actionable or at least acted upon, right? You could change your BMI through some intervention. And so there you could argue if BMI or whatever feature it was is causal of the risk that you're trying to predict, that's a different situation than if you don't know that it's causal, right? Because you might look at the risk score and see the best way for me to improve my risk is to do X.
You should never interpret a predictive model like that. You know it. You know that very well. So you also know that I'm part of the almost matching exactly lab, where we do try to use interpretable, or do try to use interpretable machine learning to predict causal estimates, treatment effects, right? So you can use the ideas from interpretable machine learning to do interpretable causal inference.
All right, thank you so much for staying an extra 25 minutes and answering all our questions. This has been a complete pleasure for us, and we hope to host you again sometime soon, and hopefully physically at some point as well. That's it for us at AI Talks, and take care, everyone. We'll see you soon.
Thank you. Bye. Bye.
Bye for now.